It's not on. There we go. First lesson, as a data scientist, you should turn on the mic or the computer, whatever you're using. I have a PhD in electrical engineering, master's in computer science, but I really got started in computers when I was around 12. And it's a funny story, but my first experience was walking into one of these stores. It was, the beginning, it was early 80s, mid-80s. And it was this whole thing about PCs, and they were going to take over the world, and it was on the cover of Time magazine and all of that. And so I remember going into one of these electronic stores and just, there was a Commodore 64, and I typed, "What's my name?" Because I thought computers would know stuff. And of course, it said syntax error. I said, "Oh, that's weird." And I said, "My name is Alex." "What's my name?" I still get a syntax error. So that was my first experience with an actual computer. And then at the time, you would buy these magazines that had a bunch of lines of codes, of numbers. Like, it had 20 lines of numbers, and you would type all these numbers, and at the end, you would get a game, right? That was the thing as a teenager. That was like an amazing thing. You would just, you buy the computer, then you buy a magazine. You sit there for 4 or 5 hours because you have nothing else to do as a teenager. And then you have this amazing game in front of you. So I did that. I bought my magazine. I got home, and I was so anxious, I just started typing. And I remember I typed for like 6 hours. And then I hit enter, and it said syntax error. And I was like, oh my God, how is this possible? So it turns out I did not read the instructions. And so the instructions said that you had to type in this program first, which would check every line of numbers and actually convert those numbers into assembly language and then code, which would run the game. So anyway, I had to do it all over again. So that's how I got started coding. So what I wanted to do today was, I've had a pretty diverse career. I've worked at a bunch of large companies, IBM, Siemens, Telefonica, Fuji Xerox, Yahoo. I was director of research at Yahoo for 5.5 years. And then I've done 3 startups. I'm on to another startup. I haven't announced it yet, so I can't say what it is. So what I wanted to do was kind of talk about lessons learned throughout all of these years of doing machine learning and data science and try to give you some insights into some of the pitfalls that I've seen a lot of people get into. Whether you're an experienced machine learning engineer or scientist or a data scientist, or you're just starting, I find the same mistakes over and over again, and I make them myself, and I find them in the companies that I join. So that's kind of what I want to do. So it's not a very, it's more of a high-level talk on some of these experiences, and I hope that you find it useful. So some of the questions that I put down on the abstract of the talk that I thought were relevant include things like, when you join a company in one of these roles, you always should ask yourself, where can I have the biggest impact? And often in data science, that's one of the biggest challenges because most of the time, nobody knows what the hell the data scientist is supposed to do, right? So it's up to you to figure out what that is. And so where can it have the biggest impact? And that's often a challenge. How to avoid those common pitfalls that occur within the context of that company or that industry. I'll talk a little bit about improvements in processes versus algorithms, because I find that most often data science or machine learning fails, and it's not so much the algorithms themselves, it's the processes, or the other way around, where you get into situations where you're working with a product team, if you're in a labs org or a science organization, and they ask you to solve a problem, and it turns out it's the wrong problem. And so part of it is understanding that process and that context. And so paying a lot of attention to process versus getting stuck on the algorithms and performance of the algorithms is really, really critical. And then there are a lot of issues around, thank you, data collection, labeling, quality. And these are pretty standard, but again, we often fail at these. And the smallest details are really, really critical. And that leads on to things like metrics, objective functions, overfitting, the cost of different types of errors. So although for most of you, I'm assuming you've heard of all this stuff, I often find that we forget, we get so caught up in our work that we forget a lot of these issues and bypass them. And that's where the biggest failures are, and that's where we miss some of the opportunities. So the way that I see it, and that I've seen it at many of the companies that I've worked at, there are a bunch of challenges, so I kind of try to make a list of what they are. Some are more recent than others. So one is the obvious knowledge gap. I meet a lot with investors, both VCs, institutional investors, CTOs, CEOs, scientists, and then people from industry at all kinds of events. And I'm often surprised to see how different the knowledge levels are and how little people know about machine learning and AI. And the level of misunderstanding is pretty significant, and it's becoming bigger and bigger as more people learn about it, but they don't really know what's going on. And I think that's something that should not be taken lightly, because in most companies, you will find that the executive teams may have no idea what a simple classifier is, right? So that's a reality, and that's something that as the field continues to grow and explode, many of us will go into companies that don't have a data science culture embedded, and they don't understand a lot of the basic concepts. So that's important. The second one is organizational structure. Where does data science sit, or research, if it's research, and within the company, is another important factor. Business alignment, which has to do with data strategy. How do you align the work that you're doing with the business metrics and what's important and what's not? And then you get into more details, like what is the computing infrastructure? One of the, I saw, I don't know if it was a survey or an article recently that said one of the hottest jobs right now is actually data engineering. It's not being a data scientist anymore, but it's being the data engineer, because a lot of data scientists are going into companies and they realize like there are no data pipelines, so they end up either having to do the data themselves, or they have to hire people to work on the data infrastructure and getting the right data in place and getting the right pipelines in. So that's kind of important to keep in mind in making career choices, and also in figuring out what you want to do. Oh. According to my phone, I am out of time. Okay, so infrastructure, and then a little bit on data quality, and then I'll go a little bit into some details on machine learning versus deep learning, and GPUs versus CPUs, because I think it's a very relevant topic today. Because one of the things that I find is, I meet people and they all want to do deep learning. They want, their company to be doing deep learning, and they all want to use GPUs. And the reality is that's not the answer for a lot of actual cases. So let's talk a little bit about the knowledge gap first. And again, I've seen this from CEOs to all the way to marketing to engineering directors who really don't understand much around machine learning. So I tend to classify people into three categories, right? So on one hand, we have the ones that think it's magic. Oh, my pointer doesn't work. Anyway, yeah, the ones that think it's magic and it'll, get everything done, and you just hire a machine learning person and throw the problem at it, and you're done. And then you have a lot of people that are really skeptical, and they say, it's completely useless. We're a small company. We don't even have data. We don't have anything. We're just building the basic products. That's so far out. We can't get anything done here. So those are the two extremes. And then there are, I would hope most of the people in this room would be kind of in the middle, right? Where we know there's a balance between the two things. It's not magic, but it's not useless. And there are a lot of situations in which it can be used. And in general, I would say, anywhere where you have data, there's repetition, and you want to make predictions, you can apply machine learning, right? If you think back of machine learning, not that long ago, when we didn't have the web at scale, like a lot of the toy problems in the UC Irvine data set, there are a few hundred elements, and you could do machine learning on that, right? So even in a small shop, you could potentially implement some machine learning if the data is collected properly, and you can learn stuff from that. So that's kind of important. So it's all about balance, understanding that balance between what you can and you can't do. And critical to this is understanding the context and the processes within that specific company, right, or industry, or whatever it is that you have, right? Because if you're working at Yahoo and you have all this, really a lot of data, That's a very different scenario than if you're working at a small startup that doesn't have data, right? So again, it'd be surprising, but and I would expect most of you to understand these differences, but I find this particular diagram to be useful in explaining what those differences might be. And so the way that I view it, so AI is a pretty large field that includes a bunch of things, and the goal is really to reach something that's almost human, right? And then you have machine learning, which is a subset of that, and it focuses on classifying or labeling instances of whatever that is. And then you have deep learning, which is a subfield of that. So just as an exercise to kind of put our feet on the ground and think about where we are. We talk a lot about AI, right? But how many times do we actually stop and think about what that means? What is intelligence? So I like looking at definitions. So I looked this up, and so the question is, what is intelligence, right? If I ask all of you, people will have very different definitions and opinions on it. But here's one, based on the Cambridge Dictionary. It's the ability to understand and learn well and to form judgments and opinions based on reason. Now, based on this definition alone, it's hard to judge whether people are intelligent often, right? Like, often people do stuff and you're like, you clearly didn't understand anything I said, and you're not forming judgments, you don't have opinions, et cetera, et cetera. If we go deeper, this is from Wikipedia, one's capacity for logic, understanding, self-awareness, learning, emotional knowledge, planning, creativity, and problem solving. More generally, the ability to perceive information, retain it as knowledge to be applied towards adaptive behaviors within an environment or context. This is really complicated. Like, just take any of those words and try to define it, right? So that kind of shows you how far we actually are from AI, and the killer robots in some sense, right? An AI that's going to replace us. Now, having said that, we have a lot of technology that's significantly better than us in many areas, and we've had it for a long time, right? Cars are faster than us. Calculators are much better than we are at adding and computing numbers, right? So it's not that technology can't be better than us in certain very specific vertical areas. That's already happened, for many decades. The difference between AI and what we're seeing now and sort of this old technology, in my view, is really that AI is increasingly influencing the decisions that we make, in terms of who we date, what we eat, the news we read and watch, how we vote, et cetera, et cetera. So understanding what that influence is becoming more and more critical. So there is a distinction between sort of the machine learning and AI technology that we're seeing today and the old technology like calculators and so on and so forth. So that's critical to keep in mind. But at the same time, to keep our feet on the ground and understand that to really build AI the way that it was envisioned initially, as something that's going to replace a human, for the most part, we need many, many fields, and I listed only 4 things, but there are many. And if we look at technical fields, it would have to use statistics, NLP, computer vision, et cetera, right? So it's really huge. So what about the hype? Let's look at the hype and why it's there. And so let's see if this video will play. I don't know if you've seen this, but and it's not all machine learning specifically, but this is work presented at CVPR, and basically what they've done is they're able to synthesize expressions through a person that's making them in front of the camera. So it's actually pretty impressive, right? Oops. Sorry about that. And as you can see from this, obviously this has pretty significant implications, right? Because you can create anything, right? And I think we're getting to that point where videos, news videos and news images that we get are going to be fake. And it's going to be very hard to determine, whether they're real or not. So that's just one example of stuff that's been, oops. Let me move to the next slide. Okay. Here's another one. I don't know if the sound, can try it. Okay, you can sort of get a sense of that. So that's completely automatically generated, right? So it's pretty impressive. And then I'm sure you've seen a lot of this kind of work, right, where you stylize, you do style transfer. And then new styles of art where you actually have algorithms generating things that look like art. And so there are a lot of questions about creativity. And I was on a panel last week, I think, at the Computer History Museum in Mountain View. And on the panel, the question came up, like, is the fact that algorithms can create things like these, is that killing creativity? What does that mean for human creativity? And my answer was, well, on one hand, they're not completely fully automatic, right? Somebody's setting the parameters and tuning these systems, so that's part of the creativity. But on the other hand, it's also raising the bar for what's creative and what's not creative. And the third thing, which is important, in the history of art, is most of the art that's been significant has been created within a certain context, cultural, historical context. So things have meanings, right? Like a Jason Pollock painting has some meaning to it, even though it looks like it was painted by a 5-year-old, right? So that's important to keep in mind. But let me just go to the next examples, and then super resolution. And anyway, there are a bunch of examples like this of where we are with the hype. Oops. Yeah. I don't know why it's not showing on full screen. Let me see. Sorry. Maybe this one. There we go. Okay, great. So there's a lot of hype. So and almost every day we're seeing these new creations from the deep learning community, if I would say there's a community. And so they're pretty amazing, right? So when people see all this stuff, it's like, yeah, it's magic. We're creating all these things. We're turning pictures of cats into pictures of dogs and generating music. And I mean, it's incredible, right? It feels like it's overwhelming to the point where people are really worried about the future of their jobs, right? And that's another point. People ask me, like, should I worry about my job? And my answer is yes, absolutely, right? Everyone's jobs will change, right? And they keep changing, and they're just changing a lot faster than they were before. Maybe the job is similar. The tools are changing. But anyway, that's a lot of the hype, and that's not going to stop. We'll continue to see a lot of really cool stuff. And in addition to like the stuff that I showed you, there are the attacks on deep learning frameworks, which are pretty amazing as well, where you take an image of a dog, and you add a little bit of noise, and then the classifier thinks that it's a fire hydrant or something completely unrelated to the dog, right? So there's a lot of development, and it's still really early on. However, in spite of all that hype and all of that amazing stuff in some specific areas, the reality, I think, is more like this. If we think of the reality of what machine learning does today, specifically in industry, it's really more like simple classifiers, applying logistic regression, using traditional machine learning to solve real business problems, right? And so one of the biggest challenges is kind of getting people to understand that gap and showing them what a machine learning algorithm actually does, and that at its essence, in terms of classification, all it's doing is trying to find that dividing line to separate two groups of items, in this particular case where you have two groups. So I think that as data scientists or scientists in any organization, our job has also shifted, and maybe in the past, when this was called just business analytics, it was fairly easy. But I think now part of our job has to be explaining to people what the differences are, right? And and I think that's really, really important to our success, you know, as in the field. Understanding and explaining those differences. Now, in terms of reality and hype, I also like to think about the failures, and I think we'll see many, many more failures as more people use this technology and we see it in more and more devices. And one thing that's really fascinating to me is how the expectations of consumers have changed over time. And if you think about it, right, like you buy a car and you expect the brakes to work 100% of the time, right? Like most of you would not buy a car if they told you, well, you know, it's 95% accurate. Sometimes the brakes don't work, but you know, it's a nice car, it looks great. But with computers, I mean, you just saw it with me, right? Oh, and by the way, this laptop, I love this laptop. I paid about $150 for it, and it looks almost like a MacBook Air, except that it has a Windows OS, and sometimes it'll try to update in the middle of my talks. So if you see that, that's what it is. But anyway, in terms of AI failures, oh yeah, what I was going to say was nowadays with like, you know, the speech-enabled assistants like Google Home and Amazon Echo, it's interesting because now we're getting used to that. It's okay if they, you know, if I say, you know, please play classical music and it starts playing classic rock, like it's okay. You know, it's not such a huge deal, right? So our expectations for how things work are kind of shifting. And that's another thing that's interesting both ways. And it's really, really important to keep in mind when you're designing these systems that whatever design decisions you make are going to have an implication when they're applied. And maybe I'm getting ahead a little bit. But it's important to try to understand that because the decisions you make, whether you're doing, you know, data science and just showing graphs or building an algorithm that's going into a product, they're really, really significant because they will impact decisions that people make, right? So keep that in mind. And the understanding that those people may have of accuracy and performance are going to impact how they use those results. So that's important to keep in mind. Anyway, so let's go into AI failures. And this is, if you've seen, I wanted to show a funny video of robots. And I'm sure some of you have seen some of these. There are so many. I spent like 2 hours just watching and trying to pick one that was short and funny enough. And I almost thought maybe I could just have robot videos while I give the entire talk, but then I thought it might be too distracting. So this one is just 1 minute, so I'll just let it play because I think it's. So I think a lot of these are not necessarily that recent, but we continue seeing these kinds of failures, right? It's fairly standard. I saw another one, I think it was in Japan, where the robot was trying to go up these stairs and it fell, so it failed miserably, and then as if it were a dead person, they brought up this thing to cover the body so that no one would see it. It was hilarious. Anyway. But thinking of failures, oops, there's my $150 laptop. Let's see. Okay. Okay, so here's a list from a paper that I found published in 2016. So 1982. They designed some software to make discoveries, and instead it discovered how to cheat. 1983, this happened again in Hawaii recently, but they had a nuclear attack early warning system, and it falsely claimed an attack was taking place. 2010, a machine learning algorithm caused a crash in the stock market, $1 trillion crash. 2011, an e-assistant was told to call me an ambulance, and it began to refer to the user as ambulance. 2015, a robot for auto parts grabbed a man and killed him. 2015, an image tagging software classified black people as gorillas. This is one example where understanding the types of errors and the impact is really, really critical. So if you use the Google API today for labeling images, it doesn't have that category, right? And recently I saw a debate on LinkedIn on this, and my opinion on that was, I mean, what's more important? Is it more important to be able to label gorilla images or to not make that mistake, right? It's more important to not make that mistake, obviously, especially for a company, but in general, there's no value in doing that, so it's better to remove it unless you reach 100% accuracy, right? So keeping those things in mind. 2016, an AI designed to predict recidivism, act at racist. 2016, game NPC design, unauthorized super weapons. 2016, patrol robot collided with a child. 2016, there was a self-driving car accident. And then, more recent one, 2016, an AI designed to converse with users became verbally abusive. So we'll continue to see a lot of that, right? That's kind of coming. But there are some simple successes, and that's another key thing, key takeaway of the talk, that a lot of the solutions in the real world don't require sophisticated algorithms. Sometimes the simplest algorithms will give us the best solution. So never assume that you need the most sophisticated algorithms to solve a particular problem. So this is ELIZA, which was developed, I think, at MIT in the 60s. And it was basically a rule-based system for having a conversation with a human. And the idea was that this system would act like a therapist. So the way that it worked is it was a very clever play of the dialogue, and it would take some of the input and just convert it into questions. And there were a bunch of rules, so it was cleverly done. So for example, I don't know if you can read in the back, but the human says, men are all alike, and then the computer says, in what way? And then the human, they're always bugging us about something or other. Then the human, the machine, can you think of a specific example? Then the human, well, my boyfriend made me come here. The computer, your boyfriend made you come here. The human, he says I'm depressed most of the time. The computer, I'm sorry to hear you're depressed. The human, it's true, I am unhappy. And then the computer, do you think coming here will help you not be unhappy? So the moral of this particular system was that it was very basic, rule-based, and a lot of people thought that it was human, and it was very successful. So just one example, but there are many examples of this, where simplicity just goes a long way, right? But now let's go back to reality. And one of the things that I wanted to talk about was organizational structure. So in any company, again, whether it's large or small, one of the things to look at and to ask yourselves is, where does data science sit in the org or research? And how close is it to the business? And what's important for that particular company, right? What is the role of the data science team? And what is your role specifically as a data scientist in whatever the processes are? So I would say there's no ideal scenario. It really depends a lot on the company. Obviously, there are companies that are very tech-focused, where they have a lot of data. And so it's clearer where things should sit. But the main thing is to have leadership alignment. So if it's a large company, one of the questions to ask is, what are the messages that the executives are conveying? How are they talking about data? How are they talking about metrics? Do they think that this is important? Is machine learning part of what they think they should be doing if they're not doing it? And are they really investing in this area or not, right? Now, if you look at the big tech companies today, Microsoft, Google, Apple, they're all talking about machine learning. And so if you join any of these, Facebook, you join any of these big companies, then it's pretty clear, right? But there are other companies that are just starting to realize that this is really important. Maybe not starting, but re-emphasizing it, right? And I read recently that I think something like 70 or 80 innovation labs have popped up all over the world in the last few years. So larger companies that say, okay, now we're going to have an innovation lab that focuses on data and analytics and machine learning. Right? Like Pepsi recently opened not recently, I think in the last 2 years, they opened like an innovation lab around data and analytics, right? And so when you see those kinds of movements taking place, that's a sign that it's being taken seriously at the overall org structure level, and that these goals are aligned with the business. So what's the level of investment, et cetera, et cetera. The second item is data, and I think it's pretty obvious, I guess, to most of us that data plays a major role in data science. But it's often one of two things, right? Either there's a lot of data, but no one knows where it is, and sometimes the data is in the typical scenario, and I'm sure many of you have encountered this. Maybe it's a large corporation or a family of companies, and they should have a lot of data. And when you look at it from the outside, yeah, like they have all the data. Like I'll just say a telecom, is a good example of that. Like they'll have all the data in the world. And then you join and you realize the data is all in silos. Different departments have different data sets. It's not well described. It's not well documented. So the challenge there is identifying which are the valuable data sets that align with the business and figuring out where you can get that. So for the most part, and in smaller startups, that implies having a data strategy. And part of your role, depending on what you're doing at the company, might be, if it's an early stage startup and you're the first data scientist, you're going to have to deal with this, and convince the executive team that they need a data strategy that includes things like policies. How much data do we retain? What do we do with it? Where do we store it? What's the infrastructure? How much money is being invested? Not only in storing the data, but in the engineering resources and the engineering support to make this data accessible. Right? What are the tools that are there, et cetera, et cetera. But whether you do that or not, if you're interviewing for a data science job, these are things you'll want to find before you join. And again, I've seen this over and over again when people join a company as a data scientist, and they're super happy, I got this job, and then they join and they realize that all of these issues are there, and they're not uncommon, right? So it's one of the bottlenecks to success, and it's not necessarily a blocker. It's just a matter of understanding where the company is when you join, and where you want to invest most of your time. So if you're a hardcore data scientist and you just want to build models and be happy doing that, and it turns out the company doesn't have a policy, doesn't have the infrastructure, doesn't have the data, then the reality is you're going to end up dealing with a lot of that before you even get to analyze any data. So it's important to understand where the company is. In terms of business strategy, and this is critical once you're in the company or before that, and it's understanding the problems that really matter for the department that you're working with or the company itself, and mostly for the company. Like in large companies, I mentioned, I don't know if I mentioned it, but I worked at Yahoo for a number of years. And at Yahoo, I was in the labs team, and the labs team were about 250 people at its peak, I guess. And we had the freedom to work with any product. And Yahoo has thousands of products at scale. And there are many products that are number one in different countries and different markets. And so picking the right product to work with wasn't always easy, like figuring out which is the right product, which one makes the most sense. And so part of the work is going to include not only, if you're given that sort of leeway to pick, in a large company, and I'm sure you would find some of the same issues at other large companies, where you're given the freedom of, you come in and you kind of have to find your own way to find the problems to work on, is understanding where the company's going and what's important. What are the priorities? What are the strategies for the company? And then finding the right product and then the right problem within that product. One of the key challenges that I've found frequently is the product managers or the product team or the engineering team working on a particular product may approach the data scientist or the scientist with a problem statement. Say, we need help with this. And then you come, and when you start talking to them, you may often realize that what they're telling you is not the actual problem, but it's a symptom of another problem. And so it's important to understand the entire process in that context. So whenever somebody comes to you with a problem, think outside of the box and go like one level higher and see where that particular problem fits within the overall process of whatever it is that the product is doing. And you'll often find that the problem is not the one that they're coming to you with, but it's something else within that workflow. So thinking of the context is really, really critical in aligning with the business partner, because you will always have, if you're in data science, you will always have to work with a business partner of some sort, right? And the other one is getting alignment of key metrics, right? That's another common mistake where, as the data scientist, you think that this is important, but the business is really worried only about that. And often a challenge is getting the businesses to understand that maybe the metric that you're proposing is more relevant to the business than the one they think that is relevant. And one example on the web might be CTR, click-through rate, right? So if you're on any website, the number of clicks on links is really critical because that basically drives number of page views and time spent, and that in turn implies an increase in revenue, right? So from a product perspective, you could say, just maximize the number of clicks, right? And there are many ways you can do that, and there are websites where you'll see that. You get all kinds of pop-up ads and a lot of garbage. So that's a metric that you could say, okay, I'm going to use this metric because that's what the business is asking me for. But if you dig deeper, you realize, and this you might get just by looking at the data, that if you do that, yeah, you will increase the CTR over a short time, but then your users will start abandoning you because the experience is so terrible that next time they come across your website, they'll just leave immediately. So you have to collect data from other metrics to support your hypotheses that metric that they're asking you to optimize is not the right one. And so a lot of it is negotiating, kind of going back and forth between what the business might be giving you and what you can get from the data in support of something else that will eventually bring you better alignment. The other question is infrastructure, right? And this is obvious. But again, there are many, many options here, and it's one of the biggest bottlenecks in data science, right? And I think for most companies today, the cloud is going to be the right answer. And so typically you have 3 tiers in the cloud service model. You have infrastructure as a service, where you have basic compute, storage, networking. And then you have the platform as a service, which is more for application developers. We have APIs and so on and so forth. And then you have software as a service, so things like Google Docs, where it's much higher level, or Office 365, right? So those are kind of the different options in terms of infrastructure for data in general. And then in terms of deployment, you can have either private cloud, community cloud, which is shared by a bunch of companies or organizations. Then in the public cloud, so the private one is only specific to that company. The public cloud, things like AWS and Google Cloud and so on, and Microsoft Azure. And then a hybrid cloud where you have a combination of the two. So in doing data science or machine learning in general, one of the options is obviously to look at the API, so the ML as a service layer. And it's often a question like, oh, should I just use the API or not? Like I gave a talk at the O'Reilly AI conference a couple of days ago, and someone in the audience was asking me like, so should I use an API or should I develop myself? And my answer was, I hate to say it, but it really depends, right, on the specific scenario and the specific use case. But if it's something like speech recognition, that's one example of that. It would be crazy for any individual developer to develop their own speech recognition system from scratch, or for a team, unless it's a huge team and they've been doing it for years. So there are some of these areas where catching up would take years and very significant effort, so it doesn't make sense to try to build it by yourself, and you're better just using the API. So examples of this are speech recognition, some image and video labeling, and some of the NLP work. So clearly, if you're doing this kind of work, you want to see what's out there, what the APIs provide. But the key thing is to see whether the outputs of those APIs match what you need, right? If the labels that are produced by the API have nothing to do with what you're doing, then that's not going to work, so you have to work harder to get it done. So if the category labels don't match your requirements, then you need to either fine-tune or want to keep, or if you want to fine-tune and have more control of what it's doing, or want to keep the data in-house, then you don't want to use these APIs. This is not a real chart, because I just filled in everything with X's, because it was easier than actually doing them one by one. But if you look at the different kinds of services through APIs that each of the major cloud providers has, there's like sort of basic machine learning services, engines, compute, data sets, and then things for visual language, search, and chatbots. The reality is, for most of these, you're going to have more than one choice, right? So you really need to look specifically at which are the most relevant for your specific use case and pick based on that. The next one is data quality, right? One key thing here is, we tend to focus a lot on the data we have, but I think sometimes paying attention to the data that's not being collected is more important. Like, look at the data you have, but think about the data that's not collected, because sometimes there's even more value in that data that's not collected. And unless the person collecting, whoever decided to collect the data was a data scientist, chances are there's a lot of data that's not being collected. So pay a lot of attention to that. In labeling data and coming up with problems or working on a problem, think really carefully about the definitions and be as specific as possible, and think about subjectivity, scalability of the process, and then any external data sources that you can use, right? Whether you have data or not, always look externally. I'll give you an example of labeling. One of the prevalent problems in almost those industries is fraud and abuse, right? If you're an online retailer, you have fraud and you have abuse. So somebody comes in and signs up with a false credit card, right? Or a credit card that looks iffy and it has a score, because you can use services that will give you a score for each credit card that say it's really reliable or it's not. Let's say from 0 to 10. So if you get a score of 5, it looks really shady, but it doesn't mean that it is, right? And if you look at data, you'll find that a lot of these credit cards that are shady, that have a 5, end up abusing the system, by ordering a lot of stuff or, whatever it is, right? So defining here whether you label that credit card just based on the score and some other metrics as abuse or fraud is pretty important, right? Because if you label it as a fraud, it means that the payment information is false. Maybe it's a stolen number, right? If you label it as abuse, maybe it's a legitimate user that's overusing the system, like it's using too many API calls. So if you mix those two, you're not going to end up with the proper distribution of the data, and you're going to tackle the problem the wrong way. So a simple mix-up in this particular case can have a significant impact on performance, whether you're trying to detect fraud or abuse. Now, another question that comes up frequently is deep learning versus traditional machine learning, right? So it's deep learning or not deep learning. That is the question. That is the new big question. And so one is understanding the differences between the two, right? And that in deep learning, you don't need to manually build the features, that the features are automatically determined by the network. But you, as the designer of the system, if you design it yourself, have to determine a whole bunch of hyperparameters, and that's typically not very easy. And then the difference between a standard neural network and a deep network, it's just in the number of layers and a bunch of other things. But it's also important, and again, this is one of those things that I find that people often misunderstand, that as in most models, you have a training phase and you have an inference phase, and they're different, and the requirements are different. And depending on the application, you may need GPUs for one and not for the other one, right? So it's not like, there's a blanket statement that says this is what you do. In general, yes, if you're using images, you want to use GPUs. But it really depends on the specific example. And the big difference in the two cases is that in deep learning, while you're training, you do multiple passes forward and backward in the network to update the weights. And during inference, you only do one. I'm out of time again. OK. So when to use which, again, it's very specific to the scenario that you're working on and the context. But in general, traditional approaches are more useful when you have smaller data sets, sometimes with a specific domain knowledge that you can encode through those features, or if you have pre-existing features. Let's say OpenCV has a bunch of feature detectors that you could use and try out fairly quickly without having to build them yourself by hand. If you need to be able to interpret what the machine learning algorithm did, then usually this is a better choice. If you're looking for savings in terms of computation or costs, financial costs, then that's important. Often the parameters are easier to tune. Training is less expensive, so you can train faster, iterate more times. And then, if you're computing at the edge, you need to look at the edge, meaning on devices and not on the cloud. Then you need to look at the cost of training versus classification, right? In deep learning, if you have large data sets, typically in the millions, not necessarily. If you could use transfer learning, that's when you take a model that's been built for something with a large training set, and then you can just take that model and use it for your own training set. So one example of that is images. A lot of models have been built to label images, and it turns out you can take some of those models. Let's say they're consumer images of cats and dogs and buildings. You can take that same model and apply it sometimes to medical images. The reason that works is because these networks learn to extract certain features like lines and edges and so on and so forth, and they learn a new class with a new training set. So transfer learning is not to be discarded, and that's a really interesting option. The drawback of that is you really kind of need to know what you're doing and understand what these networks are doing. So it may be a little bit harder if you're new to deep learning. It's end-to-end. Again, you don't need to spend 2 months designing features and building them. You can just feed in the images or the text and get an output fairly quickly. In some cases, it's been shown to have high accuracy, but you do need experience tuning all the hyperparameters and often more computational resources. One interesting thing about deep learning versus traditional machine learning, which is, again, to be kept in mind, so if it's a problem you're working on where you're going to increasingly get more data, your data keeps growing and growing, your label data, right, not just your data, but the data that you can label accurately and your ground truth can grow, then typically performance improves with that, right? Which is not necessarily true with older traditional learning algorithms. So another factor to keep in mind. So when you're approaching the problem, again, look at the specifics, look at the context. A lot of these will depend on the resources that you have. If you have a lot of money, unlimited time, usually you have either one of those two. You don't have both. But yeah, if you have a lot of money and you want to do things quickly, then GPUs are better. If you don't have that much money, but you have a lot of time, then you can use CPUs. And then you can also distribute some of these, some of the workloads, right? And there's a fair amount of work now being done on trying to distribute deep learning specifically. And think of the cost and breaking it up into training versus inference. And one of the things that's interesting is, if you train a model and it takes you 2 months to train that model, you're going to use it for a year or 2 years. I mean, that's not realistic because we tend to change them. But if performance is so great, then at the end of the day, 2 months is not a long time, right? So looking at the entire context, what percentage of your entire pipeline is training and testing and actual use or inference is important. So there are some benchmarks specifically on CPUs versus GPUs. So the main message here, and I'll show you some more graphs on this, is don't discard CPUs for deep learning, because in some cases they do work, but you have to really just try it out and understand what you're doing. So this is from a blog post from Max Wolf. And so he did a bunch of benchmarks on different problem sets, mostly smaller problem sets. But for fast text, for example, he found that training time on GPU is significantly lower than in any of the other CPU configurations. But the cost is also significantly different. So it's what I was saying before, right? Here's another example. This one, it's the other way around. On GPUs, the training is a lot longer than on CPUs. And it turns out the cost is lower on CPUs. And it's early on in the deep learning space that I think a lot of optimization remains to be seen in the software, both for CPUs and GPUs. So you need to kind of keep an eye out for both, right? Because most of the benchmarks are done just using standard implementations. And there are some implementations for CPU that are faster than the standard ones. So another example with CNN's convolutional neural networks, again, training is a lot faster on GPUs, but the cost for some configurations of CPUs are significantly lower. So if you can afford to spend more time training, then this is maybe a better option. I was at one of the talks at the AI conference was from the World Bank, and he was asked the same question. He said, well, some of this work is being done in developing countries, and they can't really afford to spend all this money on GPUs. So they're better off just running on distributed CPUs. So here are some pointers for some of the work in distributed deep learning. Intel has a framework called BigDL. There's some CTR work with TensorFlow from Yahoo. And there's a bunch of them. And then this is more of a toy problem, but you can actually run a cluster to do deep learning on Raspberry Pi 2, just for fun. I don't think you can do anything too significant with that. Okay, and I'm getting close to the end. So I mentioned processes before, and I think, again, that's really, really critical. So, you know, is the data science, you know, the math, the data that we look at and the insights, does that equal innovation? Does that equal insights? Does that equal results? In my view, the key in almost all cases is to have, you know, what I call a human-centered view on things. And it's really understanding who's going to use the system that you're building. You know, whether it's a report, whether it's a dashboard, whether it's a recommendation algorithm, what is the impact of that end user? And to do that, the way that I typically see this approach is you can start from one of these three starting points. You can start by looking at the data. You can start with a hypothesis or with the design. So if you start with a hypothesis, then you maybe make a change to a design of the algorithm, of the interface, whatever it is. Then you look at the data. Then you revisit your design or your hypotheses. And as you do this, you keep going back and forth between these three, always looking at the context and always keeping in mind who the user is of what you're doing. And the key thing here is the more you do this and the more iterations that you go through, the closer you get to the user, and that's how you actually innovate. So while you're doing that, you pay attention to the data, bias, ethics, culture, and being really interdisciplinary. And so data science is really at the intersection of user experience, data analysis, and what I call human aspects, understanding culture, memory, social status, et cetera, et cetera. And you'll find many examples in the literature. I'll just give you one quick one. In countries like Colombia, where I'm from, you pay, when you call a cell phone, you pay, the caller pays depending on the carrier you're calling. So if I have AT&T and I'm calling T-Mobile, I'll pay 50 cents a minute. If I have AT&T and I'm calling AT&T, maybe I pay 20 cents a minute, okay? And it's pretty expensive. So when you're walking down the streets downtown in Bogota, in some cities, you'll see people with big signs that say, you know, calls to AT&T, to Verizon, to T-Mobile. I'm not using the real companies' names. And then what they do is they buy unlimited plans, so they have 3 or 4 phones, one for each company, and then you pay them for the call. So let's say if you have AT&T, I said you had to pay 50 cents. So this guy will charge you 20 cents, but he has an unlimited plan, right? And so you pay him 20 cents and you make your phone call. And so it's like a human phone booth, right? So it's a pretty interesting thing. Now, I worked at Telefonica, and so when we looked at the data, yeah, it was really weird, because then we had these phone numbers that were calling many, many, many different numbers, right? And so they were like, is this a spammer? What's going on? And then, you know, related to what I was saying earlier, it's about the business decision too. Like, what do we just cut them off? Because we could, right? We could detect these human phone booths. And so it's more of a business strategy. Like, do we cut them off or do we let them exist? But anyway, that's one example where understanding the social context can be really critical in understanding the data. And there are many examples of this in terms of interface design and so on and so forth. And so design. It's not only about the interface, it's about all aspects of the system. And I think that's the most critical thing. And a lot of the failures that we're going to continue seeing in AI systems have to do with the design. You know, the data wasn't collected properly, it wasn't labeled properly. What you present, if it's a plot we did one project where we're visualizing data for the Italian elections and the US elections a few years ago on Yahoo. And it was a big deal. Like, you know, depending on how we presented the results, we could influence the elections. We were early in the game. We didn't do that. We didn't want to do that. But it was a real ethical question, right, that we as scientists should look at. Understanding the cost of errors, I talked about a little bit. And then overfitting, always trying to think, if we switch context, the data that the system is going to see is going to be completely different. So let's make sure we account for that. So these are kind of the key questions, and it's just a summary of what they are. And that's the end of my talk. So thank you very much. Feel free to connect on LinkedIn.